Right, so this is work I did with Gary here at Harvard in the Mahadevin group, and we were collaborating with Arhat, who is the expert on Darwin's finches, their evolution and development. Okay, so Darwin's finches are a classic example of adaptive radiation, and that means that they diversified from a single ancestor that arrived in the Galapagos like maybe 2 or 3 million years ago, and they diversified into 14 or 16 different species, depending on how you count. And this adaptive radiation means that they diversified into different species, but that are also adapted to different niches. And they have a wide variety of behaviors. So there's the vampire finch, which pokes into other birds and like licks their blood. And there's the paludis that uses tools, there's crushing seeds, there's probing flowers, and there's other behaviors. All right, and you can even see these Darwin's finches evolving in real time. For example, in this 40-year-old study by Peter and Rosemary Grant, they observed the behavior of these finches over a period of 40 years on a small island. And if the beak depth was not changing at all, then it would still be like inside this confidence interval. But there are in particular two events that happened where you had a sharp jump in the average depth of the beak throughout the population. And in both cases, it happened because bigger beaks can crush harder seeds faster, more efficiently. So they happened in droughts. And here, during the drought, you had less small, soft seeds that bird can eat and more hard seeds. And so the ones that were bigger were surviving more, and they were able to exploit these hard seeds. And when the population sort of crashed, predominantly the larger ones survived, and that's why we get an increase in the average depth of the beak in the population. But something happened during this period. Another species became established on this island, and when a drought happened the second time in 2005, because this bigger species, G. magnirostrus, it's actually adapted to eating bigger seeds. The competition with this resulted in a decrease in the average beak depth during this time. Okay, so they have diversified, and it seems like they're sort of still evolvable on the small scales that we can observe. And this is in contrast maybe to other birds that are on the Galapagos. They didn't diversify as much, and some of them were just one species. Some of them, like the mockingbirds, are 4 different species in about the same time, but still maybe not as ecologically diverse. So there is a question of what is it about Darwin's finches? Is there something internal in how they develop, or something external in the environment that causes them to be more evolvable? So to contribute to this, we will separate the talk into 4 different sections. So first, we want to construct a morphospace to describe the shape variation of the beaks. And then we want to see what patterns we can find in the morphospace. So looking at patterns in the morphospace, and then relating those patterns to the mechanical function of the beak. And so that's form and function. And then we want to find generative models that sort of generate the diversity of shapes of beak that we see. Okay, so previously, when people measured in morphometric studies, people sort of use discrete sets of measures like, the depth, the width, the length of the beak, and they measure it something like that. And you can learn a lot like that. Another set of procedures is to look at landmarks on here, like you have a scan of the skull, you look at landmarks on the skull, and you use those positions to construct a morphospace in which to describe the patterns of variation in the beak shape. And again, you can capture a lot about the variation, you can construct a morphospace, but here you're still missing out some information about the curvature of the beak. So you're not explicitly putting the entire shape, you're just selecting points. Okay, and again, you can learn a lot that way. There's another study that was done here at Harvard where they took images of profiles of the beak, and they had many points along the beak. So you're approximating, you're getting a lot of information about the shape of the beak. And the way they sort of quantify their shape differences is to look at, to find scaling and shear transformations that collapse the different profiles onto each other. And so by that, you can quantify how different they are, how the different profiles are different from each other. Okay, so we are sort of motivated by this. We wanted to extend it to the three-dimensional case since we have these scans, but also we want to sort of do it in a slightly different way. Okay, so our procedure is we have these scans. We start with this micro CT scan, and then we align it according to the principal directions of the beak. So that's basically the eigendirections of this, where P is just the position of the points, of the different points on the mesh. And then we cut it out. We cut, using this vertical plane, we cut out the beak. And then we align the beak according, again, to its own principal moment direction. So we align it like that, as shown here. And then we take this and we smooth it, and we close like the holes in the mesh so we can better analyze it. We also use this for analysis, and this one, but the smoother one is better for different methods of analysis. And again, we also look at this top part of the beak. We cut it out with a plane over here and a plane over there to get this mesh. And so at the end, we have a mesh that looks like that for 59 different scans from the 15 species that we have. And we want to analyze the shape of this. Okay, so to do that, we are going to look at different cross sections of it and then just see what those cross sections look like. Here we have first the mid-sagittal cross section, is shown in yellow, and we find that across all the samples we have that we could fit it very well with parabolas. So we could treat this as a parabola. And that's also what you observe, something that was mentioned here for the ground finches, but we also see it for the rest of Darwin's finches. Okay, so we can also look at the transverse cross section, since we have the three-dimensional shape, and we also find that those can be fit with parabolas that are symmetric around the y=0, where the origin is here. And so we have these parabolas, and if we look at the cross sections at different positions like that, we find that at the base, compared to the middle curve here, compared to this one, the curvature is increasing. So the curvature, the closer you get to the tip, the higher the curvature is. It's not diverging, but it's increasing. All right, so we want to look at exactly how this curvature is increasing. And what we find is that it's mostly just linearly. If the tip is over here at x=0, the magnitude of the curvature is highest at the tip, and then it decreases linearly the farther away from the tip that you go. And for this one, this is the biggest deviation from a linear fit that we found. But even here, it's still sort of the curvature as you go close to the tip is approximately varying linearly. So we can, if we take this linear fit of curvature, we still get a good approximation of the entire beak. So to summarize, what we found is that we could take this functional form, which is just a cubic. So we have this part, quadratic, which describes the yellow curve. And we have this part, these parabolas, which are describing the transverse cross sections. And we can sort of fit the shapes of the beak to this functional form. And that gives us a morphospace. So we have constant curvature in the sagittal direction. We have a linearly increasing curvature in the transverse direction. And here S is the sharpening rate, which is how fast you're getting sharp towards the center. Okay, so this gives us a morphospace, which is these three curvatures. And we can just look at what the beaks look like in this space. And the first thing you notice here, for example, the ground finches, that's Geospiza, they have higher curvature. They have lower curvature and lower sharpening rate. But these quantities, the curvatures, they're also dimensionless. They depend on the sides. So this fact that this genus, they're all lying over there, might also be related to the fact that they have on average a bigger size. So what we want is to find a dimensionless, is to look at dimensionless quantities. And so to do that, we take the same functional form, but we divide this z by the depth and x by the length and y by the width. And doing that gives us these dimensionless quantities, right? So now we can plot the morphospace again for all the samples, and we find that all the samples collapse on a plane. So it's not, in principle, it could be anywhere in 3 dimensions, but we found that they're on a plane. And at first this was surprising, but it also follows from this functional form. So if I take this condition, the z that's at length L and W over 2, that's this point over here. This point is at z equals 0 because we cut the plane, we cut the beak with the xy plane. And so taking that constraint gives us that the dimensionless curvature at the tip is 4 plus the sharpening rate. And that's the condition that we see over here. So this gives us a good check on this functional form that we found. Right, so it's an encouraging sign, and we can get another strong check on the functional form by looking at the entire cut. So this blue curve is what happens when you cut the beak by the xy plane, and the form of it can be found by this equation. We want when z equals 0 for any x, and this defines the width at that x. So the width from here to here is given by this equation. It's when this part hits 0. And again, remembering the functional form that we have, now just writing it as a depth part, which is the quadratic part, again, describing like this mid-sagittal curvature, and then the transverse part, describing these parabolas. Solving this equation just here gives us that the width is the square root of the 4 times the depth over the curvature. And so this form is not, it's not a simple polynomial, it's just you have a quadratic here and a linear function here. And if we plot it, we find that the actual curve matches the places where this mesh crosses the intersection. So we find good agreement across all the samples that we have. And this gives us an encouraging sign that we can work with this functional form to study the beaks. It doesn't mean that this is the only functional form that can fit the beaks, because again, you can fit the same mesh with different functions, depending on the number of parameters that you use. But this one is particularly nice because we just have depth, width, and length, and two curvatures, 2-dimensional curvature parameters. And all these things are interpretable. They're easy to know what we're talking about when we're discussing these parameters. So now we want to look at the fine patterns in this morphospace. So we have overall size, we have 2 aspect ratios and 2 curvature parameters. And the first thing we look at is aspect ratios. And here we notice that it actually depends on how you measure the aspect ratios. So if I align, for example, measure the beaks in a direction where I align the entire skull, for example, like that, in its own moment directions, then the beak is going to be tilted at an angle, so it's going to look like that. And you're going to get a different depth, width, and length parameters. Versus if you did it by in the natural way, where you align only according to the beak's own moment direction, and then you measure along these parameters. And so these are going to give you different results. And this is the method that's usually used, where you have where you're measuring according to like the entire head. And when we do that, we find that the aspect ratios, especially in the depth to length, which is also the thing that is evolving, that is significant parameter mechanically, this parameter is evolving from like is varying across the species from like 0.2 to 2, so it's around like 7 order, a factor of 7 from here to here. But if we measure according to this and we align according to the beak's own directions, we get a much less variation shown on the same scale here. It's just going from 0.2 to 0.3, so a factor of 1.5. So this tells us something significant, which is a lot of the variation that you might see in terms of depth over length, that might be just the variation of the angle of the beak. So if you want developmentally to grow a beak that is deeper, maybe you just grow it at an angle relative to the skull. And so this is going to play out when you're considering the mechanics of the beak. Right. In terms of curvature, we also see maybe patterns that are interesting, and also they fit what is known about the birds. So the Magnorostris, again, it eats bigger seeds and applies larger forces. And it also is the outlier when you consider the sharpening rate. And we will discuss this afterwards, that higher sharpening rates make the region near the tip more rigid. So it's less susceptible to deformation, maybe cracking. So because the Magnorostris is large, it needs to sharpen quickly so that the curvature at the beak is high enough. And that makes it more rigid. Similarly, for the Sagittal, which is the large tree finch, this one bites barks off trees and finds insects, and it needs to have a large biting force at the tip. And because of that, this is also something that we will consider in a mechanical model. It has the highest sagittal curvature. So that gives it the higher biting force at the tip. At least that's our hypothesis. And here we see that at the lower end of curvature, we have the probing beaks. These ones are insect eaters, the warbler finch. And this one is the vampire finch. So it would also have a sharp beak. All right. So another thing we can do now that we have this simple functional form is to find the affine transformations that match one beak to another. So before, in this paper, what they did was you have an optimization procedure that finds the best transformation that takes this beak into that beak. And when you have an optimization, you might worry about, are you getting stuck in local minima or something like that? And so we also had this problem when we were considering the more complicated three-dimensional matching between the beaks. And so this shows the advantage of having a functional form, because you can just do it analytically. So with these beaks, we can just fit them to parabolas and then find a scaling transformation in the x and z direction that collapses any parabola to the same functional form. So this shows an advantage of, like, if the beak is simple enough, you can fit it with functional form and then see if you can match it. So for the three-dimensional case, even though the form that we have is cubic, so it's not guaranteed that a linear transformation will match one to the other, we still find that we can do that with affine transformations, that is like scaling and shear. They could collapse all the beaks into a common functional form. Okay, so I won't use this. So this won't be like a key factor in what follows, but it just shows the advantage of having these functional forms. So now we want to look at form and function. So we have different beaks, they have different shapes, and they have also different diets that they prefer. So Magnorostris generally can eat bigger seeds and crush them faster than the Fortis. And also the small ground finch, the Fuliginosa, also eats smaller and softer seeds. Right, so we want to see if we can look at the morphospace that we have and see what it relates to these facts about the diet of the birds. So the first thing to note is that what is known is that the beak, it was correlated, the beak depth, as we shown before, was correlated with survival of the species during droughts. And it was also observed that these bigger beaks can crush the bigger seeds faster. So that is known, but exactly what advantage the depth gives you is not known, because you would need a mechanical model to sort of investigate that, especially since we saw that the variation in the depth might be just the variation in the angle. So if we said that we had like a bigger depth, that we're seeing a bigger depth in the birds, it might be that they're just having a bigger angle relative to the skull, and that's giving them the advantage. So we need mechanical models. So here, for example, they made a realistic model of the beak mechanics. So you have a scanned mesh, which corresponds to the shape of different samples. And you have here a place where the seed would be placed. And that you can find that out by observations of the birds on the ground. And you apply a force, which corresponds to the direction of muscles, that the action of the muscles. And you use the fact that here is where the beak is attached to the skull, and it's also the place where the joint is on the beak, because that's the soft part that the beaks go around. Okay, so doing that, you can simulate the forces that result, the stresses in the beak, and then you can see that a bigger depth maybe gives you better ability to avoid fracture. So it spreads out the stresses more. But again, here the study doesn't exactly tell you if it's really the depth that is doing it, or the angle, or something else, because they're just scanning the birds, the shapes of the birds, and seeing like how those, and then just seeing what forces you get. So that doesn't necessarily tell you, like if you do that and then you find that the bigger depth beak are performing better, you don't know if it's because of that or something else, because you're just correlating. Okay, so we want to, in order to sort of entangle the different aspects, you want to be able to sort of, since we have this morphospace, and then vary the different parameters in the morphospace, and then see how the mechanics of the beak varies with variation of the parameters. So we're going to do it for this simple model, which was done here to study an extinct species of birds, which is very large. So you have here, this is where the joint is, and then you have a application of force from the muscles. And so the hinge is here, that's the joint. And here is where the force is applied, and it's in that direction. And if you ignore friction, this force would be sort of perpendicular to the surface of where the beak hits. So using this, you can just do simple like moment or torque balance. So this force times the moment arm of it equals this force times the moment arm of here, of this equal to the length of this moment arm. Okay, and doing that gives you this sort of equation, which is the output force, which is here, is equal to the input force times the ratio of the moments. Right, so the longer or the shorter this length is, hm, the smaller the output force will be. The longer it is, the larger the output force. Right, so we can also just do the same diagram here. We have the direction of the application of force is along this bone, the jugal bone. We have the distance, the distance from the point of application to the joint, that's here. And we have the distance d2, which is from the joint to the seed placement. And we have then the angle from the output force to this length, and then the angle from the input force to that length. And so the same thing as we did before, d1 sine theta is the length of this arm, and then d2 sine phi, that's the length of that arm. And so we have that the output force magnitude is equal to the input force magnitude times this mechanical advantage, the ratio of the arms. And so we want to use this to understand like features of the beaks. And so what we have, so the first thing that you can notice is that the effect of the angle of the beak. So when you look at the beaks that rely on crushing seeds and have bigger forces, you'll see that these angles are closer to 90 degrees, so increasing the output force. And you also would want this phi angle to be smaller. If you look at the probing beak, that's not what you see. This one, the Scandens eats cactus, so like it probes cactus flowers, so it's not relying on strong bite forces. And you see the angle is less than 90 degrees here and larger over here. Okay, so that's the sort of simple role of angle in determining the mechanical advantage. And we can do like a more in-depth model where we treat the beak, we treat it as like this triangular shape or the tetrahedron. And so this follows the same shape as the actual beak and also taking account the angle that it has. So over here, we have the point of application of the force. That's where the muscles attach. And over here, we have the seed placement. And so we have the parameters delta and alpha that tell you where the force is applied and where the seed is placed. But we actually find that our results will not really depend on the precise value that you use. And we'll define this mechanical advantage and divide it by its maximum value so that the maximum value is at 1. So this is what we find when we do that. The interesting things to note here is that there's a weak dependence on the width over depth, right? So this mechanical advantage doesn't vary very much when you change the width over depth, which is interesting since also we find that this width over depth isn't changing very much across the species, especially for the Darwin's finches. They're all maybe over here. So they all have like a nearly constant width over depth. And this is consistent with observations that show that these width over depth is also coupled developmentally. So when you have bigger width, you get also bigger depth through like a developmental model. They're controlled by the same expression factors. And so what we see here is, other than the developmental model, we also see that there's maybe not a strong selection on this width over depth. It's not it's not pushed in a different direction because there's not a lot of variation along this axis. But there is a lot of variation along the axis of depth over length, and that's the one that you see more in evolving. And so in this case, we do see a long variation. And if you plot along this axis, where you assume this constant width over depth value of 0.5, we see that the mechanical advantage would look like this. And over here, where we have the Magnarostris, which is the bigger, it's the one that crushes the harder seeds. It's the one also that is sort of evolved to have the highest value of mechanical advantage. And you can see it saturates after that, so there's no reason for it to keep increasing. So it's sort of like taking it's almost at the maximum value that it can have. All right, so we can also look now at the role of curvatures. And to do that, we want to find something that is correlated with the diet of the birds. And it was shown here that this mechanical advantage, which is the ratio of D1 to D2, where this D2 is now the distance to the tip, this is correlated with the diet. And it's also, we would also expect it to be highest for the species that rely on a strong bite force, especially at the tip. So that's the large tree finch, which takes out bark from the trees. And so that's what we see here. And it's also large for the large ground finch and the vegetarian finch, which also is a tip biter. So it makes sense from this perspective. It also makes sense to look at from the fact that insect eaters are also the lowest in this measure. And that's because the bigger D2 is relative to D1. You have a longer beak, then you can close it faster. So the mechanical advantage sort of gives you like a compromise between stronger bite force versus faster closing speed. And so that's why the insect eaters are on this end. And so now we have this measure and it's correlated with diet. We want to see, is it correlated with different curvatures of the beak? And we find that apart from these exceptions, we find first that it has a high correlation coefficients between to the sagittal curvature. And it also has a nice trend if you exclude these insect eaters and the small cactus finch. And it makes sense because those are probing beaks and they have different pressures on them, not just biting force. And so when we look at this part, we do see a sort of a strong correlation. And in the highest scoring one, where we saw that the large tree fence has also the largest sagittal curvature. So that's this one. And the reason that we think that might be is because higher sagittal curvature would give you a higher bite force. So just a quick way to see that is that if we have this kind of arm versus just that, and you're applying the same torque here, from the green one, you get a larger force and in the perpendicular direction compared to this one, because in this case, the moment arm is larger. So the curved beak might give you a shorter arm to apply a force. And just it sort of seems similar to these kind of beaks. Okay, so another role for curvature is not just in terms of mechanical advantage, but also in terms of rigidity. And this is kind of well known for like thin shells that if you have a thin shell and then you're poking it, then the rigidity, which is sort of the force over the displacement, for a small enough force will be proportional to the curvature. And so the higher the curvature is, the more rigid it can be. And you might say beaks are not really thin shells, but they're also layered structures. So they have a layer after a layer of bone. And so this might give enhanced rigidity, especially at the tip, which is maybe more sensitive, more fragile. It would give it stronger rigidity there. And another effect of rigidity is curvature. Or another effect of curvature on rigidity can be seen here. So in this case, we have a flat paper and we apply a force. And you can see this is just like turning a page. It's very easy. But in this case, when it's curved, it would actually harder to turn pages that were curved like that. So the higher rigidity, the higher curvature we get, the higher rigidity. And so we do kind of see that in the data as well. There's a strong coefficient between the product of curvatures and the mechanical advantage. Right, and again, we can sort of have a simple simulation of an elastic shell where we apply a force at the tip and measure sort of the effective stiffness of it. And we find that it does increase overall with the sharpening rate. And this sort of gives maybe an explanation why the large ground finch had the highest sharpening rate, because it applies larger forces. Right, so now we want to look at how we can generate the beak diversity that we see developmentally. So in general, like a lot of things could be happening inside the egg that like you can have many different ways that the egg could be growing and still have the same final shape. So we need to know more about what's going on inside. And the fact that we will use is that this during development, when you have this beak growing out, there's a region at the tip where the growth is concentrated. So it's kind of growing, growing, growing. And the final shape of the tip is sort of coming out of this envelope. It's the envelope of all the growth zones over time. So to look at that more closely, you have the beak growing, and then here's where the tip is, and you have this growth zone where these cells are sort of dividing faster. And we will focus on sort of these curves, which are like right outside the growth zone, and that represents the cross section that just exited the growth zone and will be part of the final shape of the beak. And to look at it schematically, we have this growth zone. It's evolving over time, and the shape of the beak that we get depends on the shape of the growth zone over time. Right, and what we are looking to describe mathematically is just this, how these curves are changing over time, the ones that just exited the growth zone. So we have the cross section at one time, r of t, it's as we know, it's a parabola, and we have the cross section at the next instant. And what we're looking for is an expression for these green arrows, the velocities. How is the cross section changing? But the first thing to notice is that because of the beak shape that we found, we actually know that the cells, the growth zone can't just be growing uniformly. Like it can't just be scaling uniformly, because the depth, which looks like that over x, close to the tip over here, it's linear. It looks linear, so it goes like x. But the width close to the tip is like square root of x. So it looks like a square root over here. And so it's not just uniformly scaling everywhere. So cells don't just need to tell time, in a sense, to know like when to stop dividing, but they also need to know where they are. So if you're here, you're growing slower than if you're here. So to actually derive exactly how they need to evolve, we again use this simple functional form that we have, but now writing it in this way, where we introduce this sort of parameter, which will be a proxy for developmental time. So tau will be 0 at the base where growth starts, and then tau will be 1 at the tip where growth stops. And we can actually show that if you have a set of parabolas that are changing over time from one to the other, then the velocity that they satisfy has to behave like this. It has to be this constant, c minus, times the curvature, plus c plus this one times the curvature to the 1/3. So what this says is that this is any flow that preserves the parabolic shape, which is sort of what we observe for the birds, also has this functional form. So the velocity has to depend on the curvature, and it has to depend on this way, in this specific way. Right, so to look at it more closely, we have this form, and then the constants, which depend on actually exactly how the depth and the width are changing. When we work them out, they have this simple sort of time dependence. This one is increasing and this one is decreasing, but nearly constant. So with that, we have, if you have a way for the cells to tell time and a way for them to sense where they are, then this law tells you that you can recover the final observed shapes that we have. But it is actually, there's something not satisfying about this law, because there is this curvature to the minus 1/3, and you would worry about what happens as the curvature goes to 0. And so if we have kind of this form, and then the places on the parabola where the curvature goes to 0, that's like way out there. So they're not actually part of the beak. And in those places, it makes sense that a small change in the parameters of the parabola will cause us large displacements on the outside of on the outskirts of the parabola. And so if we actually plot this function for the actual beak that we have and for the range of curvatures that we observe, we find that this dependence is actually approximately linear. So we can fit it with linear dependence on curvature. So this motivates the introduction of this other growth law, which is simpler and allows us to get even more insight into the beak development. And this is called the mean curvature flow if we just had this term. And the advantage of having it is that when it's analytic in curvature, simple form, but it's also more studied and understood, and it has nice properties. So if we look at what this does is you have this initial curve. It's a little bit noisy at the beginning, but it then becomes smooth quickly, and that's because regions of higher curvature grow faster. And it also starts as non-convex, but it quickly becomes convex because these ones grow outwards, and these ones grow inside. And then it gradually becomes more and more rounder. And this is also what we see for the cross sections of the beak. So it starts like a little bit non-convex and then becomes convex and rounder. So we want to see exactly, so we want to try to fit this functional form to the beak. So we want to try to see how to fit this velocity using this form to see the behavior of the cross sections. Right, so this is what we find. We have this law, and we take the initial cross-section of the beak and as our initial conditions, and then we evolve them according to this growth law, where the velocity is proportional to curvature. And what we find is this kind of behavior in blue for the simulation, and it's compared with the gray cross-sections of the beak. And we see that there is nice agreement for a constant coefficient. And if we allowed the coefficients to be time dependent as we had before, then we would get even better agreement. Right, so we could even get even more insight by looking at the beaks, by looking at by assuming cross sections that are circular. So just the simplest form of this growth law, which turns this ordinary partial differential equations into an ordinary differential equation. And the solution would look something like that. And what we see is that we can eliminate this parameter A in terms of the length of the beak, because if A was higher, then you would get a smaller length. So we can express the parameter A in terms of the length of the beak. And for the parameter B, it actually controls what happened near the tip, because if we look here, this near the tip, R is very small, so it dominates over this term, and the solution would behave like the square root of 2b 1 minus tau, assuming that at tau equals 1, you reach the tip. And so this form we can compare directly to the width that we had before. So because they have the same functional form. So we can extract the parameter b in terms of w and kappa and s. So that's the sharpening rate, this is the sagittal curvature, and this is the width. And so these parameters a and b can directly be expressed in terms of the final shape of the beak. And then we can plot all the samples that we have, or all the species on this plot. And we see that they all lie in this blue region. And the blue region is the region that you can generate using this mean curvature flow, because for a given value of the length, if the parameter b was too high, then you would grow too fast. You would shrink too fast because b would be much too large for you to even get to that length. So you cannot sort of generate any beaks in this region. And it's interesting that all the samples that we have lie within this allowed region by the mean curvature flow. When it would have been very easy for us to violate this condition. You just have a slightly smaller sharpening rate or a slightly larger sagittal curvature, then you would not satisfy this condition. So there is something interesting going on here, because the beaks sort of occupy this region in the upper half of the allowed region. And so we have a sort of developmental constraint on the allowed parameters that you can have. So there's a sort of developmental bias in your morphospace. And this just shows that the fitting things with the circular cross-section does a good job of fitting the actual shapes of the beak. Right, so I'm going to end with this cellular level model, which sort of which tries to get the growth laws that we had before, but from a cell-based model. And we get that by assuming this sort of diffusion and degradation model. So you have each cell is producing a morphogen phi. It's coming out of here and diffusing up to there, and it decays at a rate gamma. And from the diffusion and the decay rate, we get a length scale. And that's like how much the morphogen diffuses before it decays. And so that gives you sort of this sort of communication region. And the main point of the model is that in the interior, each cell receives sort of the same number of signals from its neighbors, because it has like this circular neighborhood. All of them are producing a morphogen and sort of getting there. But near the boundary, the cell has a smaller number of neighbors at that distance. And so it will be a weaker value for phi. And at the curved, for even higher curvature, you will get even smaller number of neighbors and smaller morphogen. And so we can actually see that as long as this length is much larger than the size of a single cell, but still smaller than the size of the cross section, then near the boundary, the actually morphogen sort of behaves as it's dependent on curvature, and we see here that it achieves the curvature sensing that we would want from the mean curvature flow or the parabola preserving flow. And we can have sort of two sort of effects in the development. One is boundary depth. So if cells sort of sense the level of this morphogen and then decide to stop dividing based on it, then the cells at the boundary are the ones that are feeling the difference and then shrinking inwards. So those are the ones that stop dividing first. And the cells at the more curved end are experience even less values of the morphogen, and so they are stopping dividing even faster. So that gives you sort of the behavior that we expect from the mean curvature flow. And on top of that, we can add an effect of just cells have an internal clock and they stop dividing at random at some rate. And then, with those ingredients, we can sort of construct a model where you have these cells in the growth zone, they're diffusing, and over time they're stopping dividing, and then so because they're stopping division, the cross section are getting smaller and smaller. And again, we can recover sort of the shape of the qualitative behavior of the actual beak very closely here. Right, so to conclude, we have a functional form that sort of allows us to study the morphology of the beaks efficiently, and the functional form is easy to interpret. It expresses the things in terms of the dimension of the beak and its curvatures. And this allows us to find some interesting patterns in the morphospace of the beak and then study their functional significance. And the parameters that we find in the adult beak shape depend on the developmental model. They're constrained. They can't be sort of anything if the developmental model is correct. Right, and we still need to have more realistic studies of the mechanics of the beak with maybe finite element models, but still varying, like generating beaks based on the morphospace that we have, and seeing like how each parameter affects the beak mechanics and its function. And we also need an experimental validation of the developmental models. Right, so thank you for listening.